All right, today we begin chapter 6. This is going to be this is going to be the last section we cover. So, this is going to be, I won't necessarily say a brief overview of trig, but it's a good intro and it gets you familiar enough with the concepts that if you were to encounter them again, you'll be able to go back to this if you need a quick refresher and you can go, oh, okay, now I can do most of these trig problems that you're going to encounter. So, today we're going to start with, before we even really get into trig functions, we're just going to get into actually looking at degrees and angles and what are we going to be dealing with. So we'll start with unit circle, conversion between degrees and radians, which is very important, and I'll bring up why that's important in a bit. The commonly encountered angles, if I can enunciate correctly, arc length and angular speed, which are nice applications, and then the area of a circular sector. So a radian is represented by the Greek letter theta, and it's an angle at the center of the circle of radius 1, which we say is the unit circle. Anytime you say it has a length of 1, it has a radius of 1, those are usually like you call unit shapes. Most of the time you only encounter like the unit circle, but there is also technically a unit square. So the measurement of theta, which would be in radians, is the length of the portion of the circle subtended by theta, which is the portion of the circumference shown in green, which once we see the picture, you'll understand. And then note the unit length of the measurements is immaterial. So basically, as long as the circle has a radius of unit 1, the length of the subtended portion of the circle in the same units is defined to be a radian measure of the circle. So the amount of circle that you cover, that is the radian measure. So I said it was going to be that portion that's in green. So if you think about a whole circle is 360 degrees or 2 pi. So a full circle is 2 pi radians. And so if you ever kind of wondered, well, I know degrees and radians and all this stuff, but what do they actually mean? This is why a radian is more, I won't say it's more important to use than degrees. Degrees are nice because the numbers are a little bit easier to deal with, but a radian is an actual physical measurement of the circle. That's why with a lot of these formulas, whenever it always specifies, make sure you're in radians, make sure you're in radians. It's because degrees are only measuring an angle. The radian is measuring the physical portion of the circle. So that's one key concept to keep in mind. And the conversion formula is that 180 degrees is equal to pi radians. And so if you think about it, it makes sense because we said 360 degrees is equal to 2 pi. So thus, if you need to have a conversion, it's better just to use the reduced version because 2 times 180 does equal 2 pi. So you can cancel out the 2's. So to convert back and forth between degrees and radians, what we do is we have this unit which is pi over 180 or 180 over pi, depending on what you need to convert to. And the easiest way to remember is if you're trying to cancel out radians, pi goes in the denominator. If you're trying to cancel out degrees, 180 goes in the denominator. Because notice this would be, you could think this is 180 degrees to pi radians. This is 180 degrees to pi radians. So whatever you need to cancel, we use that conversion. And even if you, technically if you multiplied both sides here, notice 1 degree is equal to pi over 180 radians. So it makes sense if you multiply both sides by 180 over pi, you now have 180 degrees over pi is equal to 1 radian. So, and that's that one right there. So let's just do a little bit of practice converting the following. So I've got pi over 3, which is in radians, and I want this to be in degrees. So we have our pi over 3 radians. Now the question is, do I multiply by 180 over pi or pi over 180? Remember, we're trying to cancel out radians, and you have to remember that it's 180 degrees over pi radians. And so because we're trying to cancel out radians, pi goes in the denominator. And when you do that, this is a case where it's really nice because this cancels and gives me 1. And then 3 will go into 180. Let's see, it would go into 18 6 times. So it'll go into 180 60 times. So pi over 3 radians is equal to 60 degrees. Now if we start with 270 degrees and want to go to radians, then I need to go back and look at the formula. Is it going to be pi over 180 or 180 over pi? I need to cancel out I need to cancel out the degrees symbol, so I need 180 in the denominator. Now this time pi doesn't cancel with anything. But 180, so let's see, 3 would go into 18 6 times. So it's going to go into 80 60 times. And then it's going to go into 270 90 times. Which that actually works out a little bit better because those two reduce even further. Whoops. This is 3. Or this goes in 2 times. This goes in 3. And so I'm left with 3 pi over 2 radians. Now, there's only 2 ways to do these problems. Either multiply by pi over 180 or 180 over pi. And we're back to a repeat. But notice here, it's negative 2 radians in degrees. So this time we don't have a measurement that's in a unit of pi. So then the question is, okay, well, what do you do? It's still okay. I'm just going to take my negative 2 radians. And like up here, I was trying to cancel out radians, so pi needs to go in the denominator. And when I do that, you look at that and go, okay, nothing really cancels. What do you get? You get negative 360 divided by pi. That's fine. That's approximately negative 114.592 degrees. So it's just going to be represented a little bit differently. Typically, if you don't have pi in your radians, approximation is typically what you want to have, or you want to do to get at least some idea of about where it is. So negative 2 radians is almost a third of a turn around the circle. So that's kind of what that means if you want to think about it physically as like an angle that you're turning. And so I always like to talk about useful angles. This is the unit circle. What we're going to use it for is to take some what I call nice angles, because there's not really, I won't say there's not a technical name, but I just always refer to them as nice angles because they're the ones that if you plug them into a calculator, they give you a simple solution. And the reason for that is these actually, the circle or the triangles that are made from these, so you kind of think about it like this. Each one of these is making a triangle with the origin. And here's the hypotenuse of that triangle. these are the ones that give you really nice values. So even though there are square roots and they're fractions, it's better than just a infinitely repeating decimal or an infinite decimal that you're not going to get anything good out of. But kind of the main thing I want to point out is the way that these these are partitioned. Notice that it's 1, 0, and then if you go 90 degrees, it's 0, 1. If you go another 90 degrees, it's negative 1, 0. Another 90 degrees, 0, negative 1. Another 90 degrees, right back to where you started. And then for our nice angles, we have 30, 45, 60. But then notice here, this is 1/2 square root of 3 over 2. If we go 60 more degrees, we get negative 1/2 square root of 3 over 2. So this one and this one are the same thing, except with a negative in front of the 1/2. And the reason for that is the x value here, it's a circle. It's going to be symmetrical. So if I'm going 30 degrees from 90, well, notice the only thing, I'm still positive in the y direction, but now I'm negative in the x direction. So that's kind of how you can think about how these values go together. Now, I don't know the best way to put it. I'm not good enough to have this whole thing memorized. If you ask me what's the x value at 5 pi over 4 of the unit circle, I'm not going to be able to immediately just get to that. But I have enough experience with it that I've memorized the first quadrant. And the other thing, this is Q1, this is Q2, this is Q3, and yes, they do use Roman numerals. This is Q4. So I memorized the first quadrant, and that's what I recommend you do. So from the angle of 0 degrees to the angle of pi over 2 or 90 degrees, memorizing from here to here, because notice if I know this one, I go, okay, 45 degrees. All right, well, what happens if I go another 90 degrees? All right, that's 135. What if I go another 90 degrees? That's 225. And then I go, oh, well, I went a full 180 degrees from here. So that means I'm still using the square root of 2 over 2 for both of them. But it's in quadrant 3, so both of them are negative. And that's going to be a nice way that you can just reference these. And for what problems we're going to do, basically what can happen is your sector of the circle can be divided into the first third, where this is a 2-to-1 ratio because this is 30, and then you add another 60 to get to that 90. And then you can cut it in half with 45 degrees, or you can leave the larger 2/3 here, or you can just do a straight 90-degree turn. So what we're going to do is we're going to reference back to this for this next problem. So with the information that's given, we want to determine the radian measure of the indicated angle. So first we'll start with angle theta. Now, first thing you want to look at, what direction did it go? Notice this one goes counterclockwise. Counterclockwise is is a normal rotation. That's your positive rotation. Clockwise is actually a negative rotation. So when you think about this, going back to here, notice these angles are measured positive as they rotate this direction. If you were to come down here to 330, really what you would have is that it's actually negative 30 degrees. because if you do 330 minus 360, that's the value you would get. So 330, this would be negative 45 degrees. You get the idea. If you rotate clockwise, it's negative. If you rotate counterclockwise, it's positive. So if we look here, this looks like it's cutting this sector or this quadrant of the circle in half, because this goes about halfway, and then that looks to be going halfway. And I'm not going to set up anything that's like a trick or anything where it's like, oh, this is actually 46 degrees. Not trying to do that. What I do want to do is you to be able to look at this and go, okay, this looks to be roughly halfway between. So since it's halfway, you know this is going to be part of the 45 degree family of angles. So we go from 0 to 90, or we're doing radians, so we go from 0 to pi over 2 to pi to 5 pi over 4, because that's the halfway of the third quadrant. So in this case, we would have that theta is equal to 5 pi over 4. Now, we have this angle, which is not theta. This, I believe, is, it's either tau or psi. Let me do a quick double check. Sorry, this is phi, not psi. I had the p correct, but that was about it. So this is phi. Now, if we look at this one, well, this one has rotated backwards. So at the very least, I know that this is going to be a negative angle. The question, though, is what negative angle will it be? Well, there's actually two ways to determine that. We can either go around this way, or we can find the standard rotation, which might be a little bit easier. And then we can subtract it. But I'll show you how to do that. So notice this one. Part of the reason you could tell that this one is cutting it directly in half is notice that this goes right through the corner of all the grid lines. That means that this is basically, if you were to graph the whole thing out, you would have the equation y equals x. So y equals x would guide your 45 degree, or y equals negative x if it was coming from this direction. But so notice this one's a little bit above that first corner. So this is that first third. So if we go back and look, so this is a 90 degree and a 100 and another 30 degrees. So if we go back and look, this is a 120 degree angle, which means it's 2 pi over 3. So again, this is 2 pi over 3. But that's not what we're after. We're after the green angle, which is the rotation. So what you do is, if I need to go positive 2 pi over 3, then to go back around to here, I need to do 2 pi over 3. Let me use a different color. I need to do 2 pi over 3 minus 2 pi. And the reason for that is that takes me from here and makes me do a full rotation, 360 degrees, or 2 pi radians. So I go all the way around. So technically what I've done is if I'm here, I go back to here. So this would get me into if this was a single rotation. So 2 pi over 3 minus 2 pi, that's the same as 2 pi over 3 minus 6 pi over 3, which is negative 4 pi over 3. But that's only one rotation. Well, technically this is 0 rotations because this just got me into the negative. I know it's 2 pi over 3 this way, so if I subtract 2 pi, that gets me what the angle is coming from the other direction. So I need to do one full rotation after that. So for one rotation, I take my negative 4 pi over 3, and I subtract 2 pi from it, which again will be negative 4 pi over 3 minus 6 pi over 3. So that will be equal to negative 10 pi over 3 for an angle. So the way that you go about these is look at where this has landed. Did it cut the current sector you're in to where it left a third here and 2/3 here? Did it cut it perfectly in half like this one? Or maybe you'll have the opposite where you have the larger sector is here and the smaller one is here. So get familiar with this. My recommendation is either screenshot or print this slide out and just have it as a reference. It makes life a lot easier because a lot of times these are the angles that you need to be able to get to quick. So make sure, like I said, I've been doing math problems for longer than I'd like to admit at this point. So even with all my experience, I've still found it easier to only memorize the first one and then be able to get the rest of the data from this first quadrant. So memorize a quarter of the circle and I can still remember the whole thing. But that's just the way I do this. If you would rather memorize the whole circle, go for it that way. This is just the way that has helped me. Oh, and I guess I should finally write the answer for this one. That phi is negative 10 pi over 3. Now the arc length formula, it kind of makes sense when you think about it. So we have a circle with a radius r, and the length s of the arc is subtended by a central angle theta, which if you think about really what you're doing, if you were to take the area of a circle, the circumference, that's this part. This is the circumference. That 2 pi r. So theta over 2 pi is actually just like what fraction of the circle are you looking at? But since the fraction we're actually looking at is just this 2 pi, or is a certain angle theta, it makes sense that to get how long this sector is, you just multiply the angle by theta. And the angle will be in radians. Because again, the radian is a measure of the actual circle. The degrees are the angle here. So it's kind of like mixing, it's kind of like doing a bad mixture of units. So make sure that your angle is in radians, even if it's given in degrees. So the Galapagos Islands lie almost exactly on the equator. So that's them right there. I would say that's pretty darn close. They're located at 90 degrees west longitude. Suppose a ship sails along the equator from the Galapagos to the international date line, which is at 180 degrees longitude. So how far does the ship travel, and assume that the Earth's radius is 6,370 kilometers. So what information do we need to know? If we're going to figure out how far this arc length is, because what you can really think about is just take a cross section of this circle. Or of this circle. This is a globe. This is the Earth. This is the planet that we're on. So you have your radius, which is 6,370. And you're going from 90 degrees to 180 degrees. So here's our 90 degrees. And then I'm going to go to 180 degrees. And really, I want to know, assuming that we basically traveled a straight line, because if you think about it, if you go in a straight line and the Earth's... Well, you're trying to go in a straight line and the Earth is your point of reference. Drifting a few feet to the left and right is going to be practically as if you did not drift at all. So you almost get to assume here that you go in a straight line due to the negligibility of if you drift off a little bit to the left or if you drift off a little bit to the right. Now, clearly, if you just go, I don't know, like 100 miles off in one direction, yeah, that's going to cause a big effect. But so here, this is what we're looking at. Here's our theta. We have our radius, and we want to know how much or how far we traveled. So, again, observing that we're going from 90 degrees west of 0 degrees longitude to 180 degrees from 0 degrees longitude. So the 0 degrees would be off this direction. So at the center of the Earth, that would be our angle. And again, this is your cross section. So this orange line here, let me use the orange line. So this 90 lines up with here, this 180 lines up with here, and this orange lines up with this orange. So at the center of the Earth, you're starting this angle theta. So you make a 90-degree turn, or you travel 90 degrees, which is pi over 2 in radians. So through the arc length formula, 6,370 times pi over 2 is roughly 10,006 kilometers. So to travel 90 degrees along the Earth's surface, if you went in a straight line, is approximately traveling 10,006 kilometers. So, angular speed is given by, this is omega. So if it moves along an arc of a circle defined by a central angle theta in a time of t, and this could be t minutes, t seconds, whatever, the object is said to have an angular speed, which we represent with omega as the ratio of the angle to the amount of time it traveled. So this would be radian. Oh gosh, let me use a color that actually is readable on that background. This is radians per time unit. So, like, it's kind of like miles per hour, except instead of miles per hour, your distance you're traveling is actually radians, which is going over this arc. And then linear speed, which is actually how fast it's traveling, is given by the sector divided by time, which we already defined the sector formula to be r times theta, which if that's the case, then it's just r times the linear speed is just the length of the radius times omega, which makes sense. If you think about like a merry-go-round. If you're in the center, like say you were standing on the actual pivot point where the whole thing is rotating. So here's the circle, here's the center, and there's the radius. If you're standing here in the dead middle, or let's just say you were standing like right here, you're only doing this much travel, so it's not going to feel that much at all. But if you're out here near the edge, you're traveling a much further distance. So it makes sense that the radius is going to be what makes this rotational speed or the angular speed almost feel or be relatively different. So the closer you stand to the middle, because again, you're traveling, that's a little bit closer. You're going that circle versus the outer circle here. So angular speed is how fast the whole thing is rotating. Linear speed is, if you think about it, it's like what are you traveling based on where you're positioned on this disk. So suppose an ant crawls along the rim of a circular glass. It's got a radius of 2 inches, and it traverses the arc that's indicated in red below in 20 seconds. So not the fastest ant in the colony. So the questions are, what is the angular and linear speeds, and how far does it travel? So looking here, now I'm not going to jump back to it, but if you go back and you reference the unit circle, this is a full 90-degree rotation, and then this roughly does what I said of it turns it into, that's about a third of this sector, and that's 2/3. Which kind of makes sense, because if the radius is 2 inches and we've only gone 1 inch, then you have this ratio going on here. So this would actually be, this is our angle theta, this would have gone 120 degrees. And again, you can reference back to that, and you can think that if I'm here at 90 degrees and I've only got this third, then I need to add 30 degrees to get to here. But we don't need 120 degrees. 120 degrees is great for the reference angle, but I need the angular speed, which means I need theta in radians, not in not in degrees. So if I do 120, I'm not going to write rad over here just because I don't have quite enough room. And I divide that by 180, or pi divided by 180, sorry. So that's going to get me that this is equal to, so let's see, 6 would go into 12 and 18. So the easy way to think about it is they both have a 0 at the end. So if 6 goes into 12 and 18, then 60 will go into 120 and 180. So that's going to go in 3 times, and that's going to go in 2 times. So this is going to be equal to 2 pi over 3. So our angular speed is going to be 2 pi over 3 radians divided by how far, or the amount of time that the ant spent crawling, which was 20 seconds, which is equal to pi over 30 radians a second. So, and if you wanted to see what that was in degrees, well, you could just translate it back to or you could just do the 180 and that would give you an idea, or the 120, sorry. Now the linear speed, now that we have the rotational speed, or sorry, we have the angular speed, now we can find the linear speed, which again is, it's using how far away you are as a reference. So it's going to be r times omega. So r is 2 inches. And then this is going to be multiplied by pi over 30. Now the reason I'm not bringing in the radians per second is when I multiply this, I'm going to get that this is equal to pi over 15 inches per second, which pi over 15 is roughly 0.21 inches per second. Just double checking that I don't write down the wrong thing. And again, this goes back to the relative speed, or not relative speed, the relativeness of how far out are you. So it's moving at approximately 0.21 inches per second. So roughly every 5 seconds, it covers an inch of land there. But remember, because it's along this radius, it's going to be different. If this glass were to be 20 inches wide, which I think at that point you can't really call it a glass. I think that would have to be more like a bowl, I think. And then you calculated this, so you replace 2 with 20, that's moving at 2.1 inches per second. So that's a whole lot faster in terms of the relativeness of it. So just keep, the linear speed is affected by how large the circle is that you're dealing with. And then the last thing we want to do is what's the distance that it traveled. So the distance that it traveled is going to be the radius times theta, because that's going to tell you, remember, this is the arc length in radians. So this is 2 pi over 3 radians, and it has a radius of 2. So this is going to be 2 times 2 pi over 3, which is 4 pi over 3 inches, which is approximately 4.19 inches. So in 20 seconds, it covers approximately 4.19 inches, which makes sense because I said here, roughly, you cover 5 inches, or you cover an inch every 5 seconds. So it's covering just a little bit more than an inch every 5 seconds. So 5 times 4 is 20. So it makes sense that this is a little bit more than 4. But this is just kind of a nice application. It puts everything together. Like I said, you could use this same idea, but with a carousel. You start with whatever animals on the very end of the radius, and you see, okay, how far does it travel in this amount of time versus an animal that's on or closer to the inside, and you see that they both travel much smaller distances, and their linear speeds would be much different because of how far they are out relative to the center of the carousel. And this is the thing that I think I've beat over your head at this point. Arc lengths and angular speed formulas, and pretty much everything that's area or deals with this is measured in radians. It's not measured in degrees because radian is a physical part of the circle. The radian or the degrees are the measurements of the angle. So radian deals with the physicality of it, and degree deals with the actual rotation. So that's why we have to be careful about which two things we use. So then the sector area formula, which this is like saying you have a circle and you have your central angle theta. And so here's theta, but you want to know what's the area of this part of the circle. Kind of like beforehand with the arc length, which was a proportion of the circumference, a sector area is just literally going to be a proportion of the area. Because it's saying, all right, well, the area of a circle is pi r squared. Then if I take a certain fraction of that, which is going to be theta over 2 pi, then the area of a given sector is just the radius squared times the angle and then divided by 2. So say we have a circle with a radius of 3 centimeters and a central angle of 52 degrees. Like I have beaten to your head at this point, we can't use 52 degrees for measuring the physical part of the circle. We need to use radians. So first thing to do is multiply it by pi over 180 because we need to get rid of degrees, so 180 goes in the denominator, which is going to give us an angle of 13 pi over 45. This is why I say memorize the unit circle, because sometimes you don't get like this angle, 13 pi over 45. That's not going to show up on the unit circle, so just be aware. Then our area formula. So the area of a sector, is equal to the radius squared times theta divided by 2. So our radius is 3. Our central angle is 13 pi over 45, which we converted from 52 degrees. And our area is 2. Not our area is 2. And then we divide by 2 because of the formula, which this is 13 pi over 10, which is roughly 4.08 centimeters squared. Pay attention to your units. Think about this, like miles per hour, feet per second. Those are all unit over unit of distance over unit of time. Whenever you bring in a piece of the area, because you're multiplying length by length, that's why it becomes centimeters squared. Acceleration is measured in, it would be miles squared per hour. Miles per hour squared, feet per second squared, stuff like that. In this case, because it's an area, you're doing a length times a width or something like that. But area is used in units squared just because of the way things work out. And then if you do volume, which you would think of as like a box or a tube, something like that, that's going to be your units cubed because you have a length times a width times a height. So like for this one, because it's the radius squared, that's going to give you centimeters times centimeters. Let me double check the feet per second. I believe it's feet per second squared, but yes, it's the amount of time that's squared. So miles per hour, if you're talking about velocity or speed, but when you go to acceleration, it's in miles per hour squared. The hours are squared, not the miles. So that's another problem for another time, though. So then a circle of radius half a foot with a central angle of 4 pi over 3 would be the same way, except we now have one less step because we're already in radians and not degrees. So we just plug everything into the formula, and that gives us pi over 6, which is roughly 0.52 feet squared. And this is useful because think about if you're cutting out you've got a circular section of maybe a garden, or you're going to put a fountain and you need a concrete base, the fountain's circular. So you would say, okay, well, what's the circumference of the circle? And then you go, well, we're actually only going to make the fountain a semicircle. So then you go, okay, well, now I have to do this particular arc length. So now, if we do that, so that's just kind of an idea of an application of it. And so that does it for 6.1. 6.2, we'll pick up with a little bit more applications and certain things like that. Like I said, that useful angles part, highly, highly recommend either print that out, write it down in your notebook, just have it somewhere for reference. It's very useful, and it will help you out a lot in the long run.